Good morning, everyone. Nana. Yesterday we discussed about nuclear fission, I think, and in that nuclear fission concept, the energy released or the power of the reactor. Okay. So yesterday point, what we are going to recollect: power of a reactor. P is equals to, I think we got energy released for a given amount of mass. That is M into Na by capital M. These are the number of nuclei present in m grams of substance into energy released for each reaction divided by time. This one what we got, I think. Okay, using this formula here, you may solve few questions related to nuclear reactor. Okay, that is the next point you can write here. Number of nuclei in m grams of substance, m grams of fuel. Fuel means radioactive element, is equals to this one only. Okay, m into Na by m. Why? Because when we come to numericals, sometimes they only say how many number of nuclei are undergoing fission per second, means divided by t. If they give the number of nuclei, I think no need to calculate this m into Na by m. Means directly they will give it as some n number. Okay, say. Then for such type of problems, without calculating this value, directly you can use the formula power of a reactor P is equals to directly N by T, number of nuclei undergoing fission per second, into E in each reaction. Okay, this one we calculate in words. So when you come to numericals, you may use the first one to find out the power, the second one to find out the number of nuclei undergoing the fission, and here this is the power if they give straight away the number of nuclei per second undergoing fission. And E is the energy. Yesterday I told it is the energy released in each fission process. Okay, so here like to solve, like if you want to use the first equation, we need a shortcut. Why? Because all these are lengthy calculations. Okay, so that shortcut I'm giving it as one example here. Suppose if I ask, in a nuclear reactor I'm going to use 1 gram of uranium 235. Okay, and it is completely used as the fissionable fuel. Okay, is fissioned. Okay, completely. Then completely in certain time. Okay, find the energy released in the reactor. Suppose if they ask this type of question now, okay, you can use it as shortcut. If I calculate for 1 gram, then in numerical, suppose they ask 2 grams or 2 kg or like 1 ton, then you can use it as a shortcut. Okay, for that much mass, how much is the energy released? Okay, for that I am trying to solve it here. 1 gram of uranium means here in the formula, I already told M should be taken in grams only. So M is equals to, luckily he gave in grams. whereas Na, all we know, that is 6.023, approximately 6 into 10 to the power of 23. And here uranium 235, sorry, this is what mass number, molecular weight. Okay, you can represent with capital M or A nano, any letter. Okay, better we change it as Y because uh, we are tuned to that letter. So I write here capital A here, atomic mass number. Okay, right, good. Then here, if I come back to the problem, the atomic mass number, capital M or A, is 235. Okay. Then I'm asking only energy, not power. So uranium, usually they give in the problem, like in bracket, E is equals to 200 MeV or like whatever they give that value. That value you try to substitute here. Okay, E is equal to 200 MeV. Better I write here. In each fission reaction. Okay. So here, luckily, he gave the known value only. So happily, we take it as 200 MeV, but we have to convert that into joules. 1.6 into 10 to the power of minus 13 joules. 1 MeV is equals to 1.6 into 10 to the power of minus 13. Okay. Means you are getting this energy is equals to 10 per point shifting of decimal point I use. So 16 twos are 32. Sorry. 16 twos are 32, 320 into 10 to the power of minus 13 I write. This is better I write clearly here. This is 320. Okay. All right. Then I'm going back to the calculation here. I'm going to calculate the energy released, not the power. So I don't have no need to substitute the time here. Released. Okay. Here in the fission process equals to M into Na into E divided by A. If they ask the power, we take T here, energy divided by time. So I'm going to here calculate the values. So M is 1 gram. In grams only we have to substitute. This is 6 into 10 to the power of 23. Into energy is 320 into 10 to the power of minus 30 divided by A is 235. Okay. So if you do some calculation here, like 5 fours are 5 sevens, and here 5 six are 5 fours, then you will get like 6 fours are 24, 36, 38, 384 by 47 into 10 power 10 we are getting here 10 powers. So 47 approximately 50, 50 it's a 400. So this is approximately 8 times nano. So if you use if you use the calculator or using some calculation, you will get this is 8 point, I think around 17, okay, into 10 to the power of 10 joules. This is the energy released when 1 gram of uranium, that too uranium 235, and he gave luckily the energy released in each reaction on an average 200. So for such type of problem only, you can use it as a shortcut. So here that shortcut I am writing here. Note means useful particularly for MSET type of exams. Okay, there we require more time. Okay, so we need shortcuts there. So note here what I write, 1 gram of uranium, particularly 235 only, not 233, okay, 235 is fissioned completely. And one more condition here, E is equals to energy released in each fission is 200 MeV only, not changing this value like 220 or 230, 200 MeV only. Then the shortcut is, then the energy released is equals to, you can write straight away the whatever the answer you got here, that you use it as a shortcut, 8.17 into 10 to the power of 10 joules. Okay, it is a shortcut for us. You can buttify under the conditions. Mass is 1 gram, energy is 200 MeV, and the element is only 235, not 233. Okay. Sir, how to use these shortcuts? Sir, you give an example. Sure, for MSET type of exam, here, if I take one example, he is asking, bit changing, like calculate the energy released by fission from 2 grams of uranium-235. Oh, luckily we can use our shortcut. Wait for a while. 92 to 35 in kilowatt hour. Oh, not in joules, kilowatt hours. Okay, wait here. How much energy he gave there? Energy released per fission. Per fission he gave is 200 MeV. Wow, thank God. So we can use our shortcut. Okay, without calculating everything here. So directly I write, for 1 gram, I told 8.17 into 10 to the power of 10. So for 2 grams means into 2. Okay. So here you can extend, that implies for m grams of uranium-235, energy released under the same conditions is equals to, you can write 8.17 into 10 to the power of 10 into mass, whatever you are taking, joules. So here for 1 gram, this is the energy release. For m grams, same thing, into m joules energy is the energy released. So here using that shortcut, I write energy released is equals to, directly I write 8.17 into 10 to the power of 10 into mass given here as 2 grams. So into 2. So I'm getting here, this is 16.34 into 10 to the power of 10 joules. My answer is over. But actually he is asking the final answer in kilowatt hour. So in kilowatt hours means just one more step we have to take here. Okay, what is that, sir? 1 kilowatt hour is equals to 3.6 into 10 power 6 joules. And that is 36 into 10 power 5. Okay. So in kilowatt hours means this joules we have to convert. It means divided by 3.6 into 10 power 6. That's why answer is equals to, in kilowatt hours, 16.34 into 10 power 10 in kilowatt hour divided by 3.6 into 10 power 6 kilowatt hour. Okay. This one, if you do, you will get approximately 5 threes of 15. So 5 point something you will get, no, like 5.5. Sorry, you are getting 18, sorry, 4 point something. Here you will get 4 point, I think, 5 into 10 power here 4 kilowatt hour. This is the answer. Okay. This is what I said, how to use the shortcut if they ask the questions like in MSET type of exam. Okay. Suppose when you come to mains type of exams, they try to confuse you. Okay, how, sir? Like, suppose if you see the question here, you can understand. Suppose how much uranium 235? Again, he is using the fuel as uranium 235 only. Is consumed in a day. Oh, in a day means he gave the time. Time means I think he is going to ask power. He consumed in a day. 1 day means 86,400 seconds. Okay, 1 day in a day. In an in a reactor. Okay, which is operating, whose power is 400 megawatts. Okay, so here what we have to calculate, sir, in this one. Okay, megawatts, and here he said the whole uranium is converted into energy. The whole uranium is converted into energy. Okay, this one you have to understand, Nana. Okay, in a reactor, actually the fission reactions undergo, and in each fission, the parent uranium 235 will be splitted into daughter nuclei and releasing the neutrons and releases the energy. Means whole uranium 235, like the coal, is not completely converted into ash. Okay, it is converted into daughter nuclei and releasing the energy. Means one uranium disintegrated, okay, split it into two parts and releasing the energy. Means still barium and krypton fragments are there. Total mass is not converted into energy. So here he is asking differently. Here he said, consider the whole mass is converted into energy. That's why if you see this question, okay, without understanding the point what he said in the bracket, usually the student tries to solve this question like, what is there, sir, here, how much energy, how much mass? Okay, usually they give the mass and they ask the power. But this time power is given, mass he is asking. So I use my formula, sir. Power is equals to, you already gave there. That is M into NA by A into E by T, or else you gave one shortcut also, sir. For 1 gram you gave here. So here, first of all, power is equals to, using the formula energy divided by time. To use the shortcut here, I try to calculate the energy first, sir. That implies energy released in the reactor completely. Energy released is equals to, here I take it as is equals to P into T, sir, cross multiplying those two. And you will get that is equals to, power already given 400 megawatts, sir. Okay, mega means 10 power 6, we know. Okay, into that time already you said 1 day, that is 86,400 seconds. So if I multiply, this is very simple. With 4 4s are 16, 4 6 are 24, 25, 4 8s are 32, 34, 3 4 5 6. Okay, 3 4 5 6 into 10 to the power of 6 7 8 9 10. I will get 10 nana. This is the energy list. So student tries to do like, oh, what after getting this energy. Okay, he will try to solve. Sir, yeah, you gave the shortcut, sir. 8.17 into 10 to the power of 10. 8.17 into 10 to the power of 10 joules of energy you will get from 1 gram, sir. So here 3456, what a number, 3456 into 10 to the power of 10 joules, you will get from how much mass? Okay. So here, this one very simple, sir. That implies mass is equals to here 3456 into 10 to the power of 10 into 1 divided by 8.17 into 10 to the power of 10. Okay. By doing some calculation here, you may approximately get like 423 approximately you will get 423 grams we say. So if you check this one here, it will be there in options and we try to put this option. But I say, that's why I changed the color here. This is absolutely wrong now. Whatever I am going to highlight here, you did the method, this method, okay, is a wrong method. You may ask, why it is wrong, sir? Okay, see here, what he gave in the bracket, you did not understand properly. He did not say the whole uranium-235 taken in the reactor undergoes fission, is fissioned. Not mentioned here, the whole uranium-235 is fissioned. If this is the answer, it is the answer, what I am saying. If the whole uranium undergoes fission, is fissioned. Okay. But what he said here, sorry, confused here. This is uranium-235 nano. Okay, better I write here, maybe. Uranium-3235 is fission. Okay. But he said uranium-235 is completely converted into energy, means like burning the coal. Nana. Total mass is not converted into fragments. Okay. Like 5 pieces. It is completely converted into ash. Whole mass is utilized. Whole mass is utilized. Then we have to use the energy is equals to Einstein's equation, Nana. E is equals to mc square. If the whole uranium is converted into energy, then E is equals to mc square. If the whole uranium undergoes fission, keep leaving some fragments there inside the mass, okay, then we have to use this formula, shortcut formula. I think now you understood my pain here. Okay, so take care what he is asking. Energy released per fission and energy released by fission. Okay, so energy released by fission, if they ask, it is the question, it is the answer. But total mass is converted into energy, we have to use E is equal to mc square. Actually, this is not happening, but he assumed. It is a dream for a scientist. So, okay, we are just trying to calculate. Okay, we are giving the respect to avatar 1, avatar 2, avatar 3, avatar 4, avatar 5. Okay, which are not practically possible. So here you give the respect to the scientist dreams here. What is the wrong in it? So here, which is practically not possible, okay, in that, by that assumption, okay, the whole uranium-235 is converted into energy. Try to calculate what is the energy released. So I think it is not the answer. That's why, again, I'm going back to my red color. The correct answer I'm going to write here. The correct answer here is, the correct way to get the answer is E is equals to mc square. Since the whole mass is converted into energy. Now I think you understood when to use E is equals to mc square and when to use that formula. Power is equals to this one mna by A into E divided by T. Okay, or else energy is equals to m into Na by A into E. Okay, Nana? Right, take care. Better I highlight this formula also. Energy released in the reactor. I am not going to use this formula. I am going to use E is equals to mc square. In that energy released in that time, already I calculated fancy number 3456 into 10 to the power of 10. Okay, whole fancy number 3456, 10 power again 10. This is the energy in joules is equals to m into c square, you know, that is 3 into 10 power 8 whole square. Means m I am getting here 3456 into 10 power 10 divided by this one is 9 into 10 power 60. Okay, by doing some calculation here you will get like 0. Minus 6 no? Better I write 3 9 3s are 29 4 36. Okay, 384 point something you will get, Nana. Is that 27 27 means 75 9 8s are 70 exact 384 into 10 power minus 6. Okay, but keep in mind E is equal to mc square means energy in joules. This is meter per second, means both used in SI units. SI units means m should be SI unit kg. Means if I shift here the 3 decimals 0.384 into 10 to the power of minus 3 kg, that is nothing but 0.384 grams. This is the answer. Whereas 423 is not the answer. Okay, this type of confusion you can see in mains type of exam or advanced type of exam. Okay, take care. I think you understood the two differences here in the fission processes. Okay, good. Likewise, you try to calculate the energy released in the reactors, power reactors, calculating the power and energy released in the reactor. Okay. So better I go to here from the power reactor to another type of reactors so that we can complete the fission process. Okay. And keep in mind the fission you can explain with fission process can be explained already. I told, I think, while explaining fission process can be explained by using, this was previous BitSat question, Nana, by using which type of model? Already I told liquid drop model. Okay, already I told at the time of forces, while explaining the forces, that time I explained this concept. Now heavy liquid drops are identical to heavy nucleus. They are not perfect spherical. Liquid drops usually, the free liquid drop will be in the shape of sphere, but heavy liquid drops will be in the shape of like ellipsoid. Okay, like mercury, big mercury drop. Suppose when one neutron is bombarded, just like with ink pillar, one drop is added, already it is heavy, so immediately its shape will be changed. Okay, what he says, so step by step. Okay, better I write like this here. Okay, this is heavy liquid drop, like heavy nucleus, and by adding one small drop here, this is here neutron, and this is the nucleus, heavy nucleus. By adding, the shape will be disturbed, and due to the disturbance, the shape will be changed to like a dumbbell like this. Okay. And then here, because of again the surface, there the cohesive forces in liquid drop, these two try to separate from each other by considering this as one family, that as another family, and they split. Whereas in nucleus, by adding the neutron separates a few positive charges to one side, few other positive charges, means protons, to the other side. Once the neck is formed somewhere here, immediately, because of the repulsion between these two, already this is more than 3 Fermi, and here the repulsive force is the dominating force here, and directly they try to repel each other like two groups. Okay. Here these two groups immediately repel each other and will be immediately turned like this, separating the two nuclei like this. Two or more nuclei, we don't know. Okay, just one small explanation by using the liquid drop, releasing three or two or one neutron. Okay, this is the process now. So here the question is for BitSat exam, what I am saying, the fission process can be explained by which type of model? Liquid drop model. Okay, once again I am saying here the Coulomb repulsive force is identical to the gravitational force. Okay, the surface tensional force is identical to the here nuclear force. Already I gave, I think, at the time of forces concept, explaining the different types of forces. Okay, good. This is one point. Generally, what he asked, not generally, what he asked in BitSat exam previous. Okay, now I'm moving to here. What this is the story about the power reactor, where the energy is released. Okay, means to get the energy under the controlled process, controlled fission reaction. Okay, and to convert that energy for some purpose, useful energy here for us, right? Then such type of reactor where you are getting the energy is the power reactor. Okay. And particularly here, when you come to BitSat, if you use the fuel as uranium-235, okay, if the fuel in a reactor is particularly uranium-235, is uranium-235, such type of reactors are separately called as, why? Because not only uranium-235, nana, even plutonium also you can use, or uranium-233 also you can use as the fuel. So, but more frequently we use uranium-235 only. Why? Because here in the fission processes you may get plutonium or uranium-235 also. That is depending upon. Okay. So here, if you get uranium-235 here, such type of reactor is called as in a reactor. Then the reactor is called burning reactor. Some name he gave here. Okay, means his intention is you are getting compared to other elements undergoing fission like a plutonium and uranium-233. Okay, there you are getting less amount of energy in each reaction fission, like not getting 200 MeV, less energy. That's why out of those fissionable elements here you are getting more energy in the uranium-235. That's why separately he is calling it as the burning star, here the burning reactor. Okay, so it is the burning reactor where the fuel is uranium-235. Okay, this is one more point here, useful for BitSat exam, theoretical type of exam. Okay, and then I am moving to here, not power reactors, sir. There in a reactor we are not getting the energy, okay, by fission by fission, undergoing the fission. Okay, just you are transforming artificial transmutation. Okay, in this transmutation, transforming one radioactive element into another radioactive element. Okay, such type of reactor, long back I gave its name. It is called as breeder reactor now. Okay, it is the time to discuss about briefly at least breeder reactor. Okay, this breeder reactor, what is the purpose? In the reactor, main purpose of this construction of breeder reactor. In the reactor, the main aim, okay, aim of the reactor, the the non-fissionable radioactive element is converted into fissionable radioactive element. Just we are creating the proper fuel for the power reactor. Okay, that is the main aim of this breeder reactor. Okay, that is generating the fuel for whom? For fuel for uh, what we say, power reactor. Okay, this is the main motto of the breeder reactor. So here, even though the reactions undergo out of control, nothing will happen. Why? Because here you are not getting the energy. Okay, just you are transforming one to in another. So here, sir, what is the K value here, sir? What are previous present generation neutrons? No need to calculate. Okay, is the K value greater than 1, less than 1? Is it undergoing controlled chain reaction, uncontrolled chain reaction? Sir, is it actually suggestible to work in the breeder reactor as a scientist or not? Yes, you can work here in the breeder reactor happily. Okay. So in this breeder reactor, what they do, sir? Okay, actually in breeder reactor, what he is saying, next point. Here, if the fast moving neutrons are used to bombard, then such type of breeder reactors are called, then the reactor is called here fast breeder reactor. In its name only you can see fast breeder reactor. Means there you can understand fast breeder reactor means there you are using fast, means those what we are getting like a 2 MeV energy neutrons are available. Such type of neutrons if you use to bombard, not the thermal neutrons, they are called as fast breeder reactors. Suppose sir, if I use the thermal neutrons in the reactor, sir, for transmutation, okay, non-fissionable to fissionable, then that is called as in its name only, same as usual, thermal breeder reactor. Okay, so what I say straight away here, in thermal breeder reactor, I say the thermal neutrons are used. The thermal neutrons are used to bombard for the transmutation. Sir, will you give one or two examples there, sir? Yes, sure. Okay. In case of this fast breeder reactor, what you transmutates are there. Yes, simple. If you see here, I take uranium-238 as the fuel in the breeder reactor. It is bombarded with the fast neutron N01, 92-238, N01. Then first it is converted into actually uranium-92-239 and immediately disintegrated into plutonium-239 and its mass atomic number is 94. So to balance the reaction, it releases two here the beta particles. Okay, beta minus means nothing but electron. Two electrons minus here plus some small amount of energy you can see here. It is not much dangerous like in power reactor. Okay, means uranium 238 already I told many times it is non-fissionable radioactive element. It is not used for fission process. I am not able to see it clearly whether you are able to see it clearly or not. So that's why I'm changing. Yeah, now I am able to see clear. Here, plutonium 239 is fissionable. That is non-fissionable. Okay, converted into non-fissionable, but with a fast neutron, fast moving neutron. Whereas in here, if you take one example, okay, suppose if I take the thorium as thorium, I think 90, the atomic number, and 232 is bombarded with thermal neutron, not fast moving neutron, thermal neutron. This is a non-fissionable element, Nana, is converted into fissionable. That is, in this case, you are getting 92. Oh, again, here also you are getting two beta particles, two electrons. Okay, 92 and 233 here you are getting. This is also fissionable element. Okay, so here you are getting fissionable, there also you are getting fissionable from non-fissionable. Just I give two examples. Okay, Nana? This is the story, what he is saying. Okay. And suppose it is sometimes converted into uranium-235 also, Nana. Uranium-238 when bombarded with a neutron, with a fast neutron. Then 235 and 1 means 239. Thorium, sorry, in this case, what I'm saying, say, note better I write here. Uranium-92 238 is bombarded with one neutron N01. Of course, converted immediately into uranium-92 239, but very quickly it is disintegrated into uranium-92 235. Additionally, releases four neutrons here, Nana. Okay, to balance the reaction. And here you are getting sometimes uranium-235 also. Okay, then they may ask, what are these neutrons? Both the sides we are getting, both are fast moving neutrons. Fast moving neutrons, keep in mind, they are not thermal neutrons. Okay, only thing is here we are using the energy nearly 2 MeV. This is also fast moving electron, but here we are using nearly the energy around some 1.5 MeV. Means compared to this, its energy is less. That's why here transmutation is different. Okay, 2 MeV, 1.5 MeV, both are fast moving neutrons. Okay, that's why here we say use the name fast moving neutron. Okay, not using the name prompt neutrons. Okay, they are prompt neutrons means they are released in the uranium 235 process. They are prompt neutrons. Okay, this is the story about what the reactors, nuclear and nuclear fission. So by this we completed the fission process. In next class we will discuss about the fusion process. By that we can complete the nuclei chapter. Okay. Bye everyone, Nana. If you have any doubts, you can ask your doubts in the next class.